All right, so section 6.1, page 371, we're looking at finding area between two curves. So when we have been doing integration up to this point, we've been finding the area under a curve. That's what we've been calling it, where we said, like, if I wanted the integration of f of x from a to b, then that's the area under the curve of f of x from a to b. But there's another way that you could think of that. You could think of that as when I'm finding the height of these little rectangles. You know how we went through and we broke this up into rectangles. When I'm finding the height is f of x or y because the bottom function is 0. But honestly, if I were trying to find the height of this rectangle, I could say top function minus bottom function. I could say f of x minus 0 is what is leading me to that f of x. So what if the bottom function wasn't the x-axis? What if it wasn't y equals 0? And that leads us into our discussion for today, where we're looking at what if the figure instead looks like this? Well, if I wanted to find the area between these two curves from a to b, I could still use my rectangles. I could still think of this as a limit of an infinite number of sums, where I'm going through and I'm saying, okay, this is my change in x down here, but my height is just going to be the top function minus the bottom function. It's just going to be f of x minus g of x for whatever value that I choose to use out of that subinterval, left endpoint, right endpoint, midpoint, whatever. And so I could summarize that to be the integration of the top function minus the bottom function from a to b. In this particular case, the top function was f of x and the bottom function was g of x. And so I could write it in that way. And that's the formula that they give us for area between two functions. Now, we could also just use common sense and think about this in a graphic approach. All right, let's say that you're trying to find the area between these two curves, here f of x right here and g of x right here. I want to find just this little area right here between those two curves. If I go through and I find the area underneath f of x, that's all of this blue region down here, and then I subtract the area under g of x, that's all this red area, wouldn't that leave just this little piece in here in between, which I'm trying to find? Okay, then, so I can say area under f of x is just the integration, area under g of x is just the integration, and if I have two separate integrals that are being subtracted, I can combine that into one single integration that's being subtracted. So two completely different ways of approaching it, but you can see they lead us to that same conclusion. All right. Something else that you'll notice about this figure is that everything is in terms of x. A and B are my starting and stopping points, upper and lower limits of integration. They're both x values. My functions are both in terms of x, and so I'm going to have a dx at the end here as well. That's significant because in just a few minutes we're going to look at ones that everything would be in terms of y. So let's look at this first one. Example number 1, they're going to pretty much spell it out for us for this first one. It says, find the area of the region bounded above by y equals x squared plus 1, bounded below by y equals x, and bounded on the sides by x equals 0 and x equals 1. They won't typically tell us the top is this, the bottom is this, these are the sides. They don't usually do that, but for the first one, they want to make sure that we see what we're talking about. So if I've got y equals x squared plus 1, I should know what that graph looks like. That's the parabola that opens up that's had a vertical shift of a positive 1, right? So here's our standard parabola, and it's had a vertical shift of positive 1. Then y equals x, that's the diagonal line that goes through 0, 0, 1, 1, 2, 2, 3, 3. And then they tell me start at x equals 0, which is the y-axis, and stop at where x is equal to 1. So that would be a horizontal line right here at 1. When you're trying to find, as they told here, the area of the region bounded by these equations, basically what you want to do is look at what just got fenced in by those things that I drew. I mean, literally think of it like a backyard. When I drew those 4 equations or whatever, 3 or 5 or whatever they happen to give me, what just got completely fenced in, that's the region that they want me to work with, that they want me to find the area of. So in this case, it's going to be this little blue region that we've got right here. All right, so we're going to need to find A, B, and figure out which function is the top and which function is the bottom. Now, again, they were pretty clear on this one that we were supposed to start at 0 and stop at 1, so they've pretty much given us A and B in this case, although they typically won't. So I just need to know what's my top function and what's my bottom function. So what's on top, the parabola or the line? The parabola, so right, the line would be on bottom. Now, at this stage of the game, I could do a little bit of simplifying here. At this stage of the game, we're going to do all of our integration on our calculator. On the test, you will set these up only. You will not even take the time to throw them into your calculator and come up with the value. I will only be checking your setup on the test. Okay? So for these on the homework, set them up by hand, but then feel free to let your calculator do all that integration. That's a new skill that we just picked up, and I want you practicing on plugging those into your calculator. We've learned 2 ways to plug those in. You can either do it on the main screen, or you can do it on your graphing screen. Doesn't matter to me which way you do it. All right, look at example number 2. For example number 2, it says find the area of the region enclosed by the parabolas y is equal to x squared and y is equal to 2x minus x squared. Okay, y equals x squared, not too bad. I know what that one looks like. Standard position, 0, 0 is the vertex, opening up, okay? But the second one, y is equal to 2x minus x squared, I may not know exactly what that one looks like. So for that parabola, let's get some things that would help us. Probably the most helpful things are the x-intercepts and the vertex, right? So let's start with x-intercepts. How do I find my x-intercepts for this second parabola? I rewrote it in descending power order, but how do I find x-intercepts? Set it equal to 0 and solve. So I'm going to take and set the function equal to 0. I could take out a common factor of x and then set x equal to 0 and set negative x plus 2 equals 0, and I'd get 0 and 2. If I know the 2x intercepts, where is the vertex?
0. Or negative b over 2a.
If I know the 2x intercepts, where is the vertex? Halfway in between them, right? It is the midpoint. So if I know 0 and 2 are x-intercepts, where is my vertex? 1. But if it wasn't something quite that easy to work with, or there are a lot of times that, if this parabola didn't have x-intercepts, you don't always have the graph crossing the x-axis, right? If its vertex had been up here and it had been opening up, I wouldn't have had x-intercepts. So remember that you can also find the vertex by doing negative b over 2a. So what's b?
2.
2. What's a?
Negative 1.
Negative 1. So if we plug those in, we would get that same thing we found just a second ago, that the x value of the vertex is 1. And then, of course, we can plug that back into our equation to find the y value that goes along with it. So if we plug that back in, we'll get a y value of 1. So I have x-intercepts at 0 and 2 and a vertex at 1, 1. I also know that the leading coefficient is negative, so it's going to open down. So I can come over here to 1, 1 and draw my vertex, x-intercepts at 0 and 2, parabola opening down. So notice this time they didn't tell me it's this value on the left and this value on the right. I don't know what A and B are. I'm going to have to find those. And I find those by saying, what is the region that just got fenced in, that just got bounded in? What's this tiny little piece right here? How do I know where to start and stop? It is 0 and 1, but how do I know that's where I'm supposed to start and stop?
Where they intersect.
It is where my graphs intersect, yes. Now, in this particular case, I got lucky because the points of intersection were also the vertex and an x-intercept. What if that hadn't been the case? How do I find those points of intersection? Set the two equations equal to each other, right. So I'm going to take the two equations. We had x squared and we had negative x squared plus 2x. I'm going to set those two equal to each other. Thank you. I'm going to set those two equal to each other and solve. So in order to set up my integral down here, I'm going to need to know starting and stopping values, and I'm going to need to know the top function and the bottom function. So the starting and stopping values are going to come from where those two equations are equal to each other. So let's add x squared to both sides. That'd be 2x squared, and let's subtract that 2x over, so we're set equal to 0. take out a common factor of 2x, and we'll get x equals 0 and x equals 1. And so those are my upper and lower limits of integration. There's no need to take those x values and plug them back into the equation to find the y values. Remember, I just need everything in terms of x, so I don't want to waste my time finding information I don't need. All right, so which of those two parabolas was on the top? The one opening up or the one opening down? The one that's opening down, right? If we look at that, that's our top equation. So if we do top minus bottom, we're going to do the negative parabola minus the positive parabola. So the negative parabola minus the positive. And then again, I could do a little bit of simplifying. If I have negative x squared and negative x squared, that's going to be a negative 2x squared. But I'm going to throw the whole thing in my calculator, so I honestly wouldn't even have to simplify it before I typed it in. All right, let's look at example 3. Just above example 3, it says, sometimes it's difficult or even impossible to find the points of intersection of two curves exactly. As shown in the following example, we can use a graphing calculator or a computer to find approximate values for the intersection points and then proceed as before. All right, so if it's impossible, they'll give you that little calculator icon in your textbook so that you'll know which one of these they're assuming that you're going to need a calculator for and which ones that you're not. All right, so for this one, we're definitely going to need our calculator. So grab your calculator if you would. All right, so I'm going to go to y equals, and I'm going to put in my two equations. So here's the first one that we had, x over the square root of x squared plus 1, and then x to the fourth minus x. I'm also going to come over here, and I'm going to make this second graph bold, just so that you'll be able to see which one is my first graph and which is my second graph. You don't have to do that, but I'm going to do it just so that you can see it that way. All right, so now I'm going to go to a zoom. You could start zoom 6, zoom 4. I'm going to start zoom 4. So there comes the first curve, what I had in y1. And here comes the second curve, what I had in y2. All right, so I need three things. I need points of intersection, and I need to know which is the top function and which is the bottom function, right? It looks like the point of intersection here might be 0. A fast, easy way to confirm that would be to just go to our table, and sure enough, I can see both the first function and the second function that I do have zeros or x-intercepts there. So that cuts my work down in that now all I need to do is just find this point of intersection. All right. So remember that I'm going to do second trace, which is my calculate menu. I'm going to choose option number 5, which is intersect. It's going to ask me, do you want me to use this for the first curve? It's what you have in y1, so I'll tell it enter for yes. And then it jumps down and says, do you want me to use this for the second curve? It's what you have in y2. I'll hit enter for yes. Now, because there are 2 points of intersection, if you guess closer to this point, it's going to give you 0, 0. If you guess closer to this point, then it's going to give you that other one. So I'm going to be sure that I shift over there before I guess. And there is that second point of intersection, okay? So now I could go through and I could do the integration from 0 to 1.1807757. And I need to do top function minus bottom function. So what's my top function?
The y1.
y1. All right, so here's what we can do. We can quit out of this and go back to the main screen. And you'll notice that whatever you happen to have had in for x before, now when you hit x, I showed you this before, but anytime your calculator solves for an x value, it automatically stores that. So it just solved for that point of intersection where x was 1.180, so it kept that value for me. So that's nice. I don't even have to write that down. It's like my calculator auto stores that for me. So now I can go to math, and I can go down to my integration, or I can use the little shortcut, whichever you choose to do. So you can choose number 9, or remember that that shortcut is also right here in alpha F2. Nope, just kidding. My math print must be turned off. But it's right there in F2 is another place that you can get to it. Alright, so I'm going to tell it that I want to go from 0. And if I come up here and I put in X, remember it knows what that value is. It already has it stored, right? And so I can come over here and give it my equation. Now, which one did you say was on top?
Y1.
Y1. So I can just use Y1, right? Let's see if it'll use my little shortcuts now. There it goes. Y1 minus Y2. So I don't actually have to go back and retype those equations. And it'll find my area under the curve for me. Okay? So once I've done the work in the graphing screen, it's nice because it'll remember my X value, so I don't have to retype that value, and I've already got the 2 equations in there. Now, if you say, how come I don't just work on the graphing screen then? You could, but remember that what you have on the graphing screen is not Y1 minus Y2. You would literally have to go into Y equals and create a third equation, which is Y1 minus Y2, and turn it on and turn the other ones off, and then you could ask it to integrate from 0 to X, and it would do the same thing. So again, those are things that we've just learned how to do. That's why I'm telling you that you can do all of your integration by hand on here, because I want you practicing with that. So just reviewing the steps that we just did, we graphed it and got our 2 points of intersection. So we integrated from 0 to that solution point that we got. This was our top function minus our bottom function, and this was the value that we got from the calculator. Okay? So again, there'll be a calculator icon by those when they want you to use those. All right, so example number 4 says, Figure 8 shows velocity curves for 2 cars, A and B, that start side by side and move along the same road. What does the area between the curves represent? Now, if the graph is the graph of velocity and they want you to find area under a curve, what is area under a curve?
Position.
It is the position function, right? So if I'm looking at area under the curve of A and B and the difference between those, what are we talking about?
The distance between them.
The distance between them, exactly. So again, AP loves doing that kind of stuff where they ask you to look at a graph and interpret what the information means. The integration of velocity is the integration of the derivative of position, so it would take me back to the position function, and so it would give me the difference between their positions. It would give me the distance between those 2 vehicles. Good. All right, then look at example number 5. For example number 5, it says, find the area of the region bounded by the curves y equals sine x, y equals cosine x, x equals 0, and x equals pi over 2. All right? So we can go through and graph our curves, but here's the first time that we've seen this. When I graph these curves, in this first piece right here, the top function is cosine and the bottom is sine, whereas in the second piece over here, the top function is sine and the bottom is cosine. What do I do when the equations switch places? I am literally going to have to set it up as 2 separate integrals. And I need to know what this one piece is right here where that point of intersection is. Now, I could do that on my calculator, but I shouldn't need to. Remember that if I need to find a point of intersection, I can just set the 2 equations equal to each other. And so this takes us back to last year pre-cal when we solved trig equations, or you may just remember that sine and cosine are equal to each other at pi over 4, square root of 2 over 2. So that's fine as well. And so that would give us our setup then that we could say, okay, if we're going to make 2 separate integrals, for the first one, it's going to go from 0 to pi over 4, and it's going to be top function minus bottom, where in this case it's cosine minus sine. In the second piece over here, it's going to go from pi over 4 to pi over 2, and its top is the sine curve and its bottom is the cosine curve. So I literally would have to work 2 separate integrals. Now, I worked these out by hand. You do not have to. You're welcome to throw them into your calculator, but I just like to give us some repetition, particularly with our trig functions. All right, so let's look at example number 6. For example number 6, it says find the area enclosed by the line y equals x minus 1, and the parabola y squared is equal to 2x plus 6. Okay, so we start off graphing those, and we've got y is equal to x minus 1, so y-intercept down here at -1, and a slope of +1, so rise 1, run 1. Make an xy chart, however you prefer to graph a line. Graphing this parabola, though, is a little bit different. I've got y squared is equal to 2x plus 6. Might be a little easier to see that if we solve for x. So if we solve for x, we'll subtract 6 to the other side and divide by 2, and we'll get x is equal to 1/2 y squared minus 3. I can find intercepts and vertex the same way with a parabola that is opening left to right as I do with one opening up and down. For instance, I could go through here and set this equal to 0 and solve it. So I'm going to multiply both sides by 2, add the 6 to both sides, take the square root of both sides, and I'll get plus or minus 2.44 for y. So those are going to be my y-intercepts. If I set x equal to 0 and solve, the solutions that I get are y-intercepts. So I have an intercept at 2.44 and negative 2.44. Additionally, if I want to find the vertex, then I'm going to say negative b over 2a. And in this case, b was 0 and a was 1/2. So I could do negative 0 over 2 times 1/2, and I'll get 0. Plug that back into my function, and I'll get negative 3. So my vertex is at 0, negative 3. And since the leading coefficient is positive, I know that it's going to open to the right. If it had been negative, it would be opening to the left. So now I want to find the area in between these two curves right here. But here's my problem. If I go through and do what we've been doing up to this point, where I do top minus bottom, I am literally going to have to do two separate integrals like we just saw with the sine and cosine curves. Because you'll notice for this piece on the left-hand side of this line, it would be the top half of the parabola minus the bottom half of the parabola, the positive piece minus the negative piece. Whereas on the other side of this line, it would be the parabola minus the line. So I could do that. I could do it as two separate integrals. But what would be so much simpler is if I could, instead of working horizontally, if I could work, instead of doing top minus bottom vertically, it'd be nice if I could work horizontally, where I would say, okay, what is the length this way? So if I wanted to go through and find the area between two curves where my rectangles are going side to side instead of up and down, it's the same idea. I'm just going to go through and say, okay, this is my change in x, but my height is going to be the right function minus the left function. And then I would do the summation of all of my rectangles. And over here, just to avoid confusion, instead of calling these values a and b, we're going to say I'm going to start right here at c, and I'm going to sum up all the rectangles going up here to d. So that would be the summation from c to d. And to find that area, remember we said we wanted to do the right-hand function minus the left-hand function. So in this particular case, it would have been f of y minus g of y. You'll notice that c and d are y values. You'll notice that in order to say right minus left, I need to be able to say this function in terms of y instead of in terms of x. So since everything here is in terms of y, we're going to have a dy on the end as well. So c, d, f of y, and dy are everything in terms of y. So now I'm ready to find the area between these two. I'm going to need to find my points of intersection. So to find the points of intersection, I'm just going to set the two equations equal to each other. So y plus 1 equals 1/2 y squared minus 3. And move it all over to one side, set equal to 0 and solve, and I'll get y values of 4 and negative 2. And honestly, I don't have to waste the time finding the x values that go along with them, because I'm only going to need those y values for my integrand. So I can come down here and say from negative 2 to positive 4 are my upper and lower limits of integration. Now I need to figure out what's the right function minus the left function. So the right function is going to be my line, and the left function is going to be my parabola. Because if I were to draw a rectangle in here, you can see right minus left. And again, everything there is in terms of y. So we could have integrated it in terms of x if we had used two separate areas. All right, so here is our homework for tonight on pages 376 and 377. We're doing 1 through 25, every other odd, 29, 41, challenge 37.